Okay, it's time for lecture part 3 here of secondary air pollutants. You can tell I'm fading because after every 15-minute video I have to upload it, which takes about half an hour. And then I come back and make the next video, have to wait another half hour to upload. So yeah, I've been doing this a while this morning. Looking forward to finishing this one up and getting some lunch. Hope you're finding these videos informative. So let's keep moving. We got 15 minutes to wrap this one up. We are going to wrap it up on this one. So we just talked about photochemical smog. Photo, that's a good clue there that light is needed for this process, and chemical, obviously there's a lot of chemicals involved in this. Let's talk a little bit more about photochemical smog because it's going to definitely come up on the AP exam. This is a good little diagram that shows how the process kind of works. The result is this kind of yucky, almost a brownish or orangish kind of haze in the air called smog. And you usually see this over cities on bright sunny days. That makes sense because you need that sunlight for this process to happen. So you'll see that if you walk up to Corona Heights or Twin Peaks in San Francisco, you look over the bay and you can see the smog setting in there often. And that's created from ozone and particulate matter kind of combining here. And we got to remember that the ozone is created from the NOx and the VOx. And all of these emissions can put this stuff into the atmosphere. All right, just a note here that the chemical reactions are really, really complex. You can see all the oxygen radicals, the ozone here, and the O2 here, the atmospheric oxygen, and then all of these other things happening. So we don't need to know all of this. You just need to know the main ingredients, which is right there. Okay, and of course, why smog is harmful. Again, like most of this air pollution, it's going to affect our respiratory tract. Okay, increased risk of heart attacks also. Your lungs can be inflamed. You can get asthma attacks, chest pain when inhaling, or increased risk of respiratory diseases, shortness of breath. If you look at some data, some maps of asthma, where asthma is the worst. Asthma is the worst typically in cities, especially places that are close to industrial areas. And this is why, because these pollutants are being emitted into the atmosphere from these places, and it's affecting us. So if you live near these places, you're more susceptible to these diseases. All right, got that one in there. And then I love this graph. This graph shows a lot, and this is an AP exam graph. You might see this. But here you have your VOC, your VOX, and your NOx. And if we look, this is the time of day. Okay, we start at 2 a.m. and looking like we're going through the day until 6 p.m. And this is the concentration of these particular ingredients that form smog, right? So we can see here that as we go through the day, as we hit about 5 a.m., 6 a.m., your NOx and your VOX start to rise. You figure out why that is? Well, if you know that these come from vehicle emissions, it makes sense. Cars get on the road, go to work. People are getting on the road for work. There's traffic, 5, 6, 7, 8 a.m. That's why these things rise. Okay. Now, why is the ozone? Why does it take so long for the ozone to hit? You can see here the ozone peaks around 3 p.m. Well, you should also know, if you know your stuff, that ozone forms from the chemical reaction of these guys in the presence of sunlight. So you have to get these guys into the air, and then you have to have sunlight coming down. So it's this time of day that has the most sunlight. So that's why later in the day you'll get the ozone forming. All right, and that's why the smog, you'll also see the smog in the afternoon. All right, good. Hope you learned a lot on that graph. Next is temperature inversion. This is basically the final thing you need to know for outdoor air pollution, this concept of a thermal inversion. It's called an inversion because it's inverted from what the normal weather conditions are. Normally, it's warm at the surface because the sun heats the surface of the earth, as you know, and it radiates heat out. And so it's warmer the closer you get to earth. As you move up into the atmosphere, it gets colder. Right? Warm air into cold air. That's without the inversion. But add in a thermal inversion, and I'll explain why this happens in a minute. But what happens, what it is you have cold air at the bottom. Instead of the warm air being at the bottom, the warm air is on top of the cold air. It's inverted. So you have warm air at the top, cold air at the bottom. And what this does is, because it's colder way up on top, it creates air pressure pushing down on this warm air and trapping that warm air here. And because that warm air is trapped, it traps the cold air underneath. Okay, not a huge deal, but if you have a city and you have lots of emissions happening from vehicles and industry, all of these pollutants here stick around. Okay, they don't move out. So you get this temperature inversion, which traps smog. It can trap all sorts of other things here. Secondary pollutant, ozone. It can trap ozone. It can trap NOx and VOx, all sorts of things. Okay, let's move on and just talk a little bit more about thermal inversions. What causes these thermal inversions? What causes the warm air to be on top and the cold air to be on the bottom? Well, there's 4 basic reasons. One is cool, clear nights. So if you get a really cool night, the air near the ground rapidly loses its heat on a clear night. So the ground becomes cooled quickly, but the air above retains the heat from the ground, the heat that the ground was holding during the day. So it's kind of a time thing, right? During the day, it's really hot, and so the air above the surface of the earth warms, and then on a cool, clear night, the earth will get cool, but that warm air will stick around up there. So that's why you get a temperature inversion. Number 2, the upwelling of cold water can decrease surface temperature. So this is in the ocean, right near coastal areas. So coastal areas can experience a temperature inversion if they're near coast. Let me start this over. Coastal areas, cities near coasts, can experience temperature inversions because of the upwelling of cold water. So cold water coming up from the ocean near the surface, it cools the surface temperature there. Okay, so that's how you get the cold air near the surface. Meanwhile, there's warm air on top. Number 3, the topography. This is a big one, and this is, I think, what they attribute Los Angeles, why Los Angeles often experiences temperature inversions, because Los Angeles is kind of in a basin, in a valley, and so cold air flows from the mountain peaks down into the valley, and this cold air then pushes under the warm air rising from the valley. So you get warm air rising from the valley, cold air coming in off of the mountains, coming down because it's denser, cold air is denser, and so you get this temperature inversion there. And this should say number 4, snow cover. Because snow is cold, you get cold. It's cold at the surface, and its white color reflects almost all the heat coming in. So the air above is absorbing some of that reflective heat, that high albedo reflecting the heat, and the heat being absorbed by the air, so it's warmer on top. Okay, you can tell I'm running out of steam here, so let's keep moving. All right, moving on to indoor air pollution. The main thing here we want to know about is radon. Radon is a gas that can get into your home and cause some serious problems. Toxic gas. We learned about uranium when we talked about nuclear energy. Well, uranium occurs, as we know, in different places around the Earth, and it's in rocks, in certain places. Uranium is unstable, so over time it decays, and over time it decays into radium and then into this gas called radon. And it's this radon that can sneak into homes. So let's take a look at how it enters a home. Well, radon can be found in fractured bedrock. So if there's cracks in the bedrock, it can kind of work its way through the cracks, and it's a gas, so it rises, right? So it's always going to find a way up. So it can find its way up into the soil, so your soil can have radon in it. Or maybe it gets into the basements and can leak into the basements, or it can also get into groundwater. And so if you have a well and you're using groundwater to drink or to shower, it's getting into the groundwater. And all different ways that this radon can kind of creep out of the soil, out of the rock, and go up. And if you build a house on top of where the radon's coming in, it's not good. This just shows you where the geologic radon potential is. Where is the most potential for radon? And high is in the pink. So definitely the upper Midwest here and the upper West and along the Appalachians. San Francisco, it's not too bad here. And radon is responsible for 21,000 lung cancer deaths per year. And that averages out to 58 deaths per day. So it's pretty dangerous, this radon stuff. It says nearly 1 out of every 15 homes in the U.S. is estimated to have elevated levels of radon. Do you have a radon detector in your house? All right, we're going to wrap up here in 2 minutes and just tell you that there's lots of different toxicants that are in the home. So you can take a look at these. You can pause the video. I'm not going to go through them all, but you should be familiar with some of these. And some of these we already have covered under organic pollutants and where they occur in the home. All right, and the final thing, just want to talk to you about exposure and dose, because the effects of pollution, what pollution does to us and does to animals and plants, is a matter of exposure and dose. So exposure is the concentration, how much of the agent is at the boundary between the individual and the environment. So exposure, how much am I being exposed to? And then the final thing is the dose. That's how much of it is actually entering over a specific time period. Okay, so this is a great little diagram here. It shows the environmental conditions. You're exposed to the pollutant, and then it gets in you in certain ways, either by touching, like by your hand, or it gets on your skin, or you eat it, or drink it, or you breathe it in, right? Those are the ways it gets into us. And then dose is the bioavailability, the genetics, the susceptibility, all of that determines the dose. That means how much of it we can take in, our particular genetics that is prone to this kind of stuff or not, how susceptible we are, what do our immune systems look like, all of this kind of stuff contributes to the dose. Last thing I want to say is just it's important to note that many effects of pollution are not acute, they're rather cumulative. So know these words: acute, that means it's showing up immediately, and cumulative, it builds up over time. So most of this air pollution stuff builds up over time. It's not necessarily acute. And here are the groups that are particularly at risk, and this is obviously true, and true also with COVID too, right? Elderly, not necessarily young kids for COVID for some reason, but the elderly, those with weak immune systems, etc. All right, a couple of videos you could watch on my lectures. Bye, guys. Good job.